Why economists love the Cobb-Douglas function? Ever wonder why some production functions are more popular than others? So let's talk about the Cobb-Douglas function. What's the most versatile tool in an economist's toolbox? For modeling how inputs like capital and labor turn into output, it's often the Cobb-Douglas production function. But why this function makes so special? In this video, we are going to explore of its superpower, flexible return to scale, and its famous constant elasticity of substitution. Let's break it down. The Cobb-Douglas production function is famous for being the first neoclassical production function developed for its widespread use in economics. And it's famous because it is very simple, empirically verifiable, and has useful mathematical properties. So the function of Cobb-Douglas production function is showing us that Q equal to function of capital and labor, and which is representing with a coefficient of capital A, and here we can see the degrees of freedom of K is A and degrees of freedom of L is B, and the value of capital A, small a and small b is less than 0. And in this function, Q is representing the total output, and capital A is presenting the factor of productivity. K is representing input as capital, L is another input as a labor, and small a is the elasticity of capital, and B is the elasticity of labor. The Cobb-Douglas function is flexible return to scale and famous constant elasticity of substitution. The first key property is its return to scale. What if we double all our inputs? Let's scale about K and L by factoring T. We plug Tk and Tl into the function. After factoring, we see the output is scaled by t to the power a plus b. There is incredibly flexible. And if we see the conditions of a and b, where a plus b is equal to 1, then it means the constant return of scale, double inputs and double output. And if the value of a plus b is less than 1, it's increasing return to scale, doubling inputs more than double outputs. If a plus b is less than 1, it's decreasing return to scale. And this is flexibly allows economies to all sorts of real world industries, which can shows with the scales and the values of a plus b. So here is the graph which is showing us the constant return of scale occurs when output increase in the same proportion as the increase in inputs. So if all factors are increased by a same rate, the constant return to scale is also called a linear homogeneous production function. After that, we are seeing the increasing return to scale, which is occur when output increase in a greater proportion than the increase in inputs. If all factors are increasing by 20%, that output increased by say 30%. So the doubling the factors, output increased by more than double. So this is our graph with capital and labor, which is showing the increasing return to scale. After that, we will see the decreasing return to scale when the value of a plus b is less than 1. So this is our graph. Decreasing return to scale occurs when output increases in a lesser proportion than the increases in inputs. All the factors are increased by 20%. Then output increases by less than 20% actually. So after that we will see the linear function. Cobb-Douglas production function is a simple linear logarithms, and in this logarithm we can see that function ln q is showing a function with ln a and small and also small a is showing the elasticity of output with respect to k, and if we see the elasticity, then that will be partial derivative of q and partial derivative of k. After that we can see the elasticity of b, and which represent the elasticity of labor, and this is the proportion. The proportion is ln q by ln n, and both of is representing the partial derivative. The second great features is the Cobb-Douglas in linear in logarithms. By taking the natural log of both sides, we get this simple linear equation. This isn't just a math trick, it's a huge practical advantage. The coefficient of a and b now have a direct economic meaning. They are the output elasticities, and this makes illustrating the function with real data much simpler, and we can prove the proof starts with the MRTS, which is the marginal rate of technical substitution. The slope of this isoquant, which is a model, and it's the ratio of the marginal products. Let's calculate the marginal product of labor, which is the partial derivative of q with respect to L. And next, the marginal product of capital. Now the MRTS is marginal production of labor divided by marginal production of capital, and we can see that as term the term cancel out beautifully with, and also a cancel out beautifully, and there the k term simply just a k in a numerator. The L term simplified to 1 by L, and we left with the elegantly simple formula. The MRTS equals to B by A and times to capital labor ratio K by A. Okay, the simple linear relationship is the key actually. To find the elasticity, we work with logs. Taking the natural log of both sides give us the linear equation. Now let's rearrange it as solve for ln k by L. So there is the elasticity, which is sigma. It is formally defined as the percentage change in capital labor ratio divided by percentage change in the MRTS. And look at our equation. Ln k by L is a linear function of ln MRTS, which showing the slope is 1. So the derivative of a variable with respect to its is always 1. Therefore sigma equals to 1, and it's straightforward. So we can see the Cobb-Douglas function, where the function is showing us widely why that is used. So we can say that Cobb-Douglas production function actually used for its return to scale captured by a plus b, and its elasticity of substitution n that is constant at 1, meaning that labor and capital are imperfect but which is flexible in substitutes, and it is a simple, flexible and powerful for modeling economics. Thank you so much for watching. Leave a comment below if you have any question or suggestion for what we should explore next. So until next, keep learning. Don't forget to subscribe my channel and press the bell icon. Thank you. Tada!